Scene script. Have you ever wondered how digital circuits function? It's an intriguing world that operates on logic and design, a world that defines the rhythm of our digital age. As we delve into the fascinating realm of engineering, digital circuits stand as a cornerstone, and to understand these circuits, we need certain tools. Two fundamental concepts that help us understand these circuits are maps and frames. Intrigued? Let's dive in. Maps in digital circuits, or more commonly known as Carnot maps, are not your regular geographical maps. They don't lead you to hidden treasures or picturesque landscapes. Instead, they guide you through the intricate maze of digital logic design. But before we dive deeper, let's start from the basics. Imagine a truth table. It's a simple, straightforward way to represent the relationship between inputs and outputs in a digital circuit. But as the number of inputs increases, truth tables can get a bit unwieldy. That's where Carnot maps or K-maps come into play. K-maps are essentially graphical representations of truth tables, but they are not just for show. They serve a critical purpose. They help to simplify Boolean algebra expressions. And why is that important? Well, the simpler the expression, the fewer logic gates you need in a circuit. In other words, K-maps help to minimize the number of logic gates. Now, you might be wondering, what's the big deal about reducing a few logic gates? Well, fewer logic gates mean less complexity, less power consumption, and less chance for errors. It might seem like a small thing, but in the vast world of digital logic design, every gate counts. So how does a K-map do this magic? It groups together the ones or zeros in a truth table in a way that allows us to simplify the Boolean expression. This grouping is based on adjacency and can span across the edges of the map, making K-maps a bit like a torus, a donut-shaped surface. But don't worry, we won't be venturing into the realm of topology today. To sum it all up, Carnot maps are a powerful tool in the arsenal of every digital logic designer. They help transform complex, gate-heavy circuits into simpler, more efficient ones. So, in essence, K-maps help us in making complex circuits simpler and more efficient. While Carnot maps help in simplifying the circuit, frames ensure that the circuit operates correctly. Now, let's turn our attention to these frames, the unsung heroes of digital circuits. If you think of a digital circuit like an orchestra, frames are the conductors. They ensure that every component, every signal, plays its part at the right time. You see, in the world of digital circuits, timing is everything. Signals need to be synchronized, and operations need to happen in a specific order. This is where frames come into play. They represent the timing and sequencing of digital signals in a circuit. Imagine a series of digital signals, each with its own rhythm and tempo. Without a frame, these signals would be like a band without a conductor, each instrument playing its own tune, oblivious to the others. The result? A cacophony of noise, not music. In a similar way, in a digital circuit, without frames, signals would be sent and received at random intervals. There would be no synchronization, no order. The circuit might work sometimes, but it would also fail unpredictably, making it unreliable. But frames bring order to this chaos. They synchronize the signals, ensuring that each one is sent and received at the right time. They set the rhythm of the circuit, dictating when each operation should occur. Think of it like a well-rehearsed dance. Each dancer knows their cues, knows when to step forward, when to spin, when to leap. That's what frames do for digital circuits. They ensure that each signal, each operation knows when to step forward, when to spin, when to leap. So while Carnot maps might get all the glory for simplifying circuits, let's not forget the vital role that frames play. They ensure that the circuit not only works, but works reliably, efficiently, and predictably. And that's why, without frames, the digital circuit would be a chaos of signals, with no synchronization or order. Now that we understand maps and frames, it's time to see how they interact in a digital circuit. In the intricate world of digital logic, maps and frames are the dynamic duo, working harmoniously to ensure an efficient and correctly functioning circuit. Let's delve into this fascinating interplay. Carnot maps, or K-maps as they are fondly called, are the architects of our digital circuit. They take the cumbersome truth tables and transform them into a simplified graphical representation. This simplicity is not just for aesthetics, but it plays a crucial role in minimizing the number of logic gates in a circuit. Imagine a city map. It helps us find the shortest route to our destination, doesn't it? Similarly, K-maps help us find the simplest expression for a Boolean function, the shortest route to designing our digital circuit. But what good is a well-designed circuit if it doesn't operate at the right time? Enter frames. If K-maps are the architects, frames are the timekeepers of our digital world. They ensure that the signals in a circuit are synchronized, maintaining the rhythm of operations. They control the timing and sequencing of digital signals, ensuring that every part of the circuit dances to the same beat. Now, when these two come together, they create a symphony. K-maps simplify the circuit design, and frames ensure that this design operates in perfect harmony. They are like the two wheels of a bicycle, both equally important for the smooth ride of our digital circuit. It's a beautiful dance, really. K-maps streamline the complexity, and frames keep the rhythm. They ensure that the digital circuits are not just functional, but efficient and reliable. It's a dance that happens in every digital device around us, from our smartphones to the most advanced supercomputers. So, the next time you use a digital device, remember the silent choreography happening within, orchestrated by the interplay of maps and frames. Together, maps and frames make the digital world go round. Theoretical understanding is good, but where are maps and frames used in the real world? You might ask. Well, let's dive in and explore. Maps and frames, particularly Carnot maps and timing frames, have become indispensable tools in various fields, playing significant roles in the development of modern technology. In computer engineering, for instance, Carnot maps are employed extensively to simplify logic circuits. These maps help in reducing the number of logic gates in a circuit, leading to more efficient and cost-effective designs. So, when you're working on your laptop or playing a game on your console, remember there's a K-map somewhere in there, ensuring everything runs smoothly. Similarly, timing frames are crucial in the world of telecommunications. They are used to synchronize digital signals, helping to prevent data corruption during transmission. Think about it. Every time you video call a friend or stream a movie online, timing frames guarantee that the data packets arrive in the right order at the right time, providing you with a seamless experience. But the application of maps and frames doesn't stop there. Even in the realm of robotics, these tools have proven invaluable. Robots, as you might know, require precise timing and control of digital signals to perform tasks. Timing frames ensure that robotic movements are synchronized, while Carnot maps simplify the logic circuits controlling these movements. Moreover, in the broader scope of electronics, these concepts have been instrumental in the development of digital clocks, calculators, and even traffic light controllers. So, you see, maps and frames are not just theoretical concepts confined to textbooks. They are real, practical tools that engineers and designers use every day to create the technology we rely on. They're the unsung heroes working tirelessly behind the scenes to make our digital world efficient, reliable, and enjoyable. So the next time you use your smartphone or laptop, remember the maps and frames working behind the scenes. Before we wrap up, let's summarize what we've learned today. We've delved into the intricate world of digital logic and design, shedding light on two crucial elements, maps and frames. Carnot maps, or K-maps as they're commonly known, provide us with a graphical representation of truth tables. Their primary purpose is to simplify Boolean algebra expressions, reducing the number of logic gates in a circuit. This simplification process isn't just a neat trick. It's a vital step in designing efficient, effective digital circuits. Next, we explored frames. These are not just static pictures, but dynamic timelines that represent the sequencing and timing of digital signals in a circuit. They ensure the synchronization of signals, a critical factor in the correct operation of every digital circuit. The interplay between maps and frames is fascinating. K-maps help in minimizing the logic, while frames ensure the smooth running of that logic over time. It's like a well-choreographed dance where each move is critical to the performance as a whole. And let's not forget the practical applications. From your smartphone to your laptop, from traffic lights to space rovers, these concepts are at play in every digital device around us. And that's a wrap. Keep exploring, keep learning, and remember, every digital device you use is a testament to the magic of maps and frames.